Okay, folks, how are things going? Any lab report questions? Feel like the lab reports are coming together okay? Is there adequate resources for knowing sort of what's expected in there and how they should look, that kind of thing?
Yes, yes.
Okay, cool. Any other logistical questions for anyone? Yeah.
I have a quick question about the lab, like the code submission thing. So when we like pasted our code into our like lab report, it added like 15 pages to it.
That's, yeah, so I'm asking for all of you to include your source code as an appendix to the lab report. Just the source file, incidentally, so just your .c that contains main and your threads and such, which will indeed extend the length of that report considerably, but since we're turning all these in electronically anyway, that's okay. But then we can see your code and just make sure it's well commented so that I and your TAs can navigate it. Yeah?
A better idea of how to do that on
A better idea than just copy pasting into a Google Doc. I know that there do exist software packages for creating like a nice listing. Do you have
There's a like Google Docs extension called like code blocks that'll kind of format it for you.
Okay. Sound good? The other thing that I'll just briefly mention, I put an announcement on Canvas. There now exists an EdSTEM page for the course. I haven't used this service before, incidentally, but it seems like one that folks are familiar with. So I think this is the replacement to Piazza, so that folks can ask questions to one another and answer one another's questions. Okay, so what I want to talk about today, so last time we talked about the implementation of the Boyd's algorithm. We talked about the algorithm itself and how it works. What I'd like to spend time discussing today is the demo code from which you will start your checkouts this week. And I want to point to the places where you will likely insert the Boyd's algorithm into that demo code. And then I want to talk in a little bit more detail about how, with time remaining, I want to talk a little bit about UART. And I'm going to use a particular Bruce addition to Protothreads for UART printing as a mechanism to sort of explain in a little bit more detail how UART's working. It's one of those things that we've been using under the hood the whole time to call things like printf, and it's kind of useful, I think, to just take a moment to describe how that protocol actually works. So let me pull up the lab write-up for this week. Incidentally, I've been reading back through this, and it occurs to me that, so the expectation for your lab checkout this week is one Boyd flying around the screen. You might find that you achieve that relatively quickly. If you do, I'd really encourage you to try to get as far as you can on the week 2 checkout. Getting one Boyd to fly around the screen, I think with pretty modest changes to the demo code, you can get that working. Getting the whole algorithm working on a small flock of Boyds is significantly harder, and I think you will thank yourself if you sort of get as far as you can on this next checkout this week. We can help you do that. Okay, so what I want to take a look at is the demo code, and in particular, I want to look at the lab2 directory, the animation demo, and animation.c. Some folks have gotten this running already, correct? So when you get this running, what this is actually doing is just animating 2 balls bouncing around the screen, and then there's a serial user interface through which you can indicate a number. You can enter a number between 0 and 7, and that number maps to a color, which allows for you to change the color of the balls that are bouncing around the screen. So this is what you'll start with, and then you'll modify what this is doing so that instead of animating 2 little bouncing balls, it's instead animating as many Boyds as you possibly can. But I want to start our discussion of this just by scrolling down and taking a look at main. What we'll find actually is this demo, there's less going on in this demo than there was in the Lab 1 demo. That's partially by design. The notion of this class is that as we go along, we step back a little bit more each time and give you a more and more pared down skeleton to start from so that you can build on it more substantially. This is moving you towards final projects. So there's less going on here than there was in Lab 1. If we look at main, the first thing that we do is initialize stdio. And as we've talked about, this allows for us to do things like call printf. It sets up the default UART channel on UART channel 1. We initialize the VGA. I'm going to talk in detail about the way that the VGA works, I think on Friday and then into next week. This lab, it's often the case with lab 2 that we get about a week of time where folks are debugging and we can talk about bugs that folks are having here in lecture, but there's also some opportunity for us to pop down a level of abstraction and remove some mystery around things like how the VGA is actually being operated and things like that. So I think we'll take the opportunity end of this week and next week to talk through that. But in any case, we initialize the VGA, we reset core 1 and then launch core 1, and then we add a couple of threads to our scheduler and start the scheduler. And if we look at our entry point on core 1, all that core 1 is doing is adding a single thread to its scheduler and then starting the scheduler. So I want to take a look at each of these threads, and let's start with one of the threads that's doing animation. So let's take a look at this particular thread, Protothread anim for animation, and talk through how this is actually working. As I mentioned last time, in order for the animation to look correct, what's really important is that you are updating the thing that you're animating, the void, the ball, whatever it is, at a really precise frame rate. And in this particular demo, the frame rate to which we're adhering is 30 frames per second. So 30 times a second, we go in, erase the previous position of the ball, compute its new position, which depending on its speed may or may not leave it at the same pixel, or it may move it to an adjacent pixel, or a pixel's a few pixels away, a place a few pixels away. But in any case, 30 times a second, we go in, erase the ball, compute its new position. In this case, the set of rules by which we're computing that new position is really simple. It's just bouncing around. Your set of rules will be the whole Boyd's algorithm. And then we're redrawing it. And then we're waiting for however long we need to wait in order to have that all happen again precisely 33 1/3 seconds later. So if we look at this particular thread, we start with a PT begin as usual. We then declare 2 static ints. This is something to remember this lab. This lab, I hope, is going to clarify the utility of protothreads. It's going to be a protothreads intensive lab. And I'll just remind you that one of the bugs that many of you will likely bump into in working with protothreads is forgetting to declare any local variable in a thread as static. So let me just briefly remind you that protothreads, as we've talked about, is a stackless threading library. That means there's no stack associated with each of these threads. When a particular thread yields, what's actually happening is the function that defines that thread is exiting. And when that happens, all the local automatic variables declared for that function are popped off the stack and they disappear. So by declaring these variables that are local to this thread as static, what we're doing is we're telling the compiler that we would like for these variables to have local scope. Will be scoped only to this thread, the function that declares that instantiates this thread, but they'll be stored as global variables, which means that when we come back to this thread, they will have retained their values, the same values that they had when we left them, which is what we want. So in any case, we declare 2 static ints, one called begin time and one called spare time. Incidentally, I'm going to show you 2 ways to enforce this animation rate. One uses a PT yield for a certain amount of microseconds. The other one uses an augmentation to protothreads that Bruce added that is PT yield interval that does what I'm describing sort of under the hood. But we'll talk about both to help clarify how this is working. So in any case, we declare these two local variables. We then call a function called spawn Boyd. This does what you would think, but we could just go take a look at it for a moment. What spawn Boyd does is initialize a handful of state variables associated with that Boyd. Remember that each Boyd is specified by 4 states. Its x position, its y position, its x velocity, and its y velocity. In this case, we're saying our particular Boyd is going to have an x position at 320 pixels, a y position at 240 pixels. So that is to say it's going to be in the middle of the screen. And then we give it some initial x and y velocity. In particular, well, there's an argument to this particular function that allows for us to specify if we want for its x velocity to be in the positive or right direction or the negative or left direction. So in any case, this instantiates x, y, vx, and vy for a particular Boyd. And then the first thing that was, I'll just briefly remind you that The stuff above the while one loop is all the initialization stuff. This runs the first time that we schedule the thread. All the stuff in the while one loop is what gets scheduled over and over and over again. So the first thing that we do when we enter this while one loop is we make a call to a C SDK function time microseconds 32, which some of you used last lab in order to time your cricket chirps. I'll just remind you that what this is doing is accessing the lower 32 bits of that 64-bit incrementing microsecond timer. So in line 170 here, we're figuring out what's the value of this timer right now as we're entering this thread. The next thing that we do is we draw a 2x2 rectangle, well, it's a square, but a rectangle that's 2 pixels on each side over the X and Y position of that void that we just instantiated, and we're making that rectangle black. We're erasing the void. So at the beginning of this thread, the void that we are updating was at position void 0x, void 0y, and it was some color, whatever color you specified. But because the background of the VGA screen we have is black, if we draw a black rectangle over the void, we're effectively erasing it. And we're doing so in a time-efficient manner. We are only manipulating the specific set of pixels that we need to in order to make that void disappear, as opposed to erasing the whole screen, right? Which would take more time. So we erase the void. We then call a function called walls and edges, which we can take a look at. But what this is evaluating is the position of the void, and it's looking at the position of the void, and it's asking, did this void leave the boundary within which we want for it to bounce around? And if so, reverse its X or Y velocity in order to bounce it back towards the interior. So we just take a look at this quick. We can see that walls and edges takes the X and Y position of the void and its velocities. If it hit the top, which is to say its Y position has exceeded its top threshold, then we reverse its Y velocity, and we increase its Y position by just a little bit. Why might we do that? If it exceeds the Y velocity, if it goes above the boundary in the up direction, you would think that just reversing the Y direction is Y velocity would kick it back down towards the correct part of the screen, right? Why is it a good idea to also increase its Y position a little bit? Thoughts? Yeah.
Might get stuck on the outside of the rectangle.
Exactly. So suppose your void's moving kind of quickly in the up direction. So in a particular frame, it bumps, a handful of pixels above that boundary, and then you reverse its velocity, and it doesn't quite make it back to the other side of the boundary. Then the next frame update, you're going to reverse its velocity again, and it ends up just bouncing around up here above the boundary. If we give it just a little kick back down towards the center of the screen, it makes that behavior much more rare. And likewise for all the other sort of barriers, right? So if we leave any boundary, then we reverse the appropriate velocity component and give it a little boost back towards the center. So that is it is this line here that's updating our position and velocity. If we look back, sorry, I'm going to scroll just back up for just a second. You can see that the other thing that happens in this function is, so we update our velocity as needed, and then we use our updated velocity to update our position. So suppose we reversed our X velocity, then we would say our new X position is given by our old X position plus our new X velocity. Updating our position velocity, yeah.
I just feel it's a bit odd to choose a constant for the kick. Aren't you supposed to depend on like maximum velocity so that you can type this constant more?
Yeah, that little kick will not probably be relevant to you when you actually modify this into voids. Because what you do when a void leaves a particular boundary is not going to be reverse its X or Y velocity. It's going to be instead to add or subtract a little bit from the appropriate velocity component by that turn factor. And so what will happen is the void leaves the boundary, and instead of bouncing back, as in this demo, it'll instead do sort of a nice organic curve back towards the center. So we've updated our position, we've updated our velocity. So we got the time, erased the void, updated the void's position and velocity. We then redraw the Boyd. So we're drawing a 2x2 rectangle now over its new X and Y position of whatever color we've specified. And then this is the mechanism by which we enforce the frame rate. We then say our spare time, the amount of time for which we would like this thread to yield before it is scheduled again, is given by our frame rate as measured in microseconds. So 33 1/3 milliseconds becomes what? 33,000 microseconds. So it's our frame rate minus our current time, the time that we measure after having gone through this process, minus the time that we measured when we first started doing the Boyd update. So in effect, what we're saying is we would like for this thread to be scheduled at this designated frame rate. In order to do that, we want for this to yield for the frame rate time minus the amount of time that we spent in the thread doing Boyd position and velocity updates, right? So the exercise in lab 2 is to drive this as close as you can to this. That is to say, to spend as much time as you possibly can updating your flock, updating the biggest possible flock that you can without exceeding your frame rate. And then we yield for however many microseconds is required in order to come back exactly 30 hertz. Does that make sense? Yeah.
What if that's like a negative number? Like if spare time is negative, what will happen?
What do you think will happen?
If it throws an error, it doesn't call it at all.
It does not throw an error. It will allow for you to do this. Yeah.
Doesn't like it repeat or something? I forget what the exact thing is, but if it's negative, it'll like repeat for protothreads and yielding. Am I thinking of a different thing?
So I believe the symptom of this is I believe that let's see. I believe that a negative number will be interpreted by PT yield microseconds as a very large positive number. I think, in which case the flock would kind of stop. I think that's the symptom. Do you agree with that, Bruce?
I think that's right. I can't remember whether it's an id or u.
We can check a little bit later on in the lecture, but we'll take a look at this in just a second. But it might be a wise idea to just do a quick check to see, is this indeed positive? And if it's negative, to make it 0. Yeah.
But if it's negative, you know you're no longer meeting the conditions of the lab, and you might want to put a message on the screen.
It'd be a wise idea to provide some indication as to whether or not you're meeting the timing deadline. For the checkout, I'm going to ask for that, for some indication. And it could be printing a message to the screen. It could be something associated with the LED. Maybe you turn the LED on if you ever exceed, 30 frames a second. You could set a GPIO port. You could do whatever you would like to do, but there should be some indication as to whether or not you're meeting the timing deadlines. The reason being that if you drop just a little bit short of it, it can be difficult to tell visually. And I understand that part of the flavor of this lab is cheating and trickery. This I want to enforce. This is the one sort of thing that I don't want for anyone to cheat, is the frame rate. I don't want for your frame rate to ever drop below 30 frames a second. Anything else, cheat. Okay? And then we yield for the appropriate amount of milliseconds. So for you all, right, this is updating the position and velocity of a single particle. For you all, what you'll do instead is come into this thread, grab the time, and then for every Boyd in the flock, you will go through and update that particular Boyd's X position, Y position, X velocity, and Y velocity. So there will be some loop here, right, where you loop through every Boyd, you erase that particular Boyd, you implement the algorithm for updating that Boyd's position and velocity. It updates its position and velocity by looking at all the other Boyds and seeing what they're doing, and then moving as appropriate if Boyds are too close or if they're in their neighboring range. And then you redraw that particular Boyd, and then you go to the next one and the next one and the next one, and you do as many as you possibly can before you run out of time. is this going to be constant?
Well,
Spare time?
depends on,
For a given flock size, do you expect to have a constant amount of spare time in your animation loop? If you think back to the algorithm. I'm seeing heads nodding no. The answer is no, right? And the reason is that if you remember from our discussion last time, the way that this algorithm is working is every Boyd is looking at the position of every other Boyd. That remains constant. But then there's a whole sequence of actions that only get taken in the event that there are other Boyds in either the protected range or in the visual range. If there are no Boyds in a particular Boyd's protected or visual ranges, then that update for that Boyd is comparatively fast because you're skipping a whole section of that algorithm. If, on the other hand, there's a lot of Boyds in each other's protected ranges or visual ranges, then every Boyd is going through the whole algorithm and it costs you more time. So what you'll see if you have some sort of real-time indication of your spare time in your animation loop here is what you'll see is as the flock is sort of moving across the screen, you may have a considerable amount of spare time because they sort of spread out as they go across. As they get to a wall or a corner and they start to turn back around, they're going to cluster, and you'll see this drop. And what I'm asking for is that this never drops below 30 frames a second. Questions about that? And in this particular example code, so we were looking at the animation thread on core 0. You can see that core 1 is also scheduling a similarly named thread. So actually, we may have been looking at the one on core 0. But in any case, essentially an identical thread is also running on core 1 that is also independently animating its own ball. So when you run this demo, there are two balls bouncing around the screen. One of those balls updates is being done by core 0, the other is being done by core 1. So when you're first getting started, what you might consider doing is just try to get Boyds running, just try modifying, say, the thread on core 0 so that it animates a little flock of Boyds, and deschedule the one on core 1 if you want to. Or just focus on one of the cores. And then maybe an interesting next step is you put an independent flock on each core so that you have, and give them different colors, right? So that you can tell. Maybe you have a blue flock on core 0 that's flying around, and each Boyd is changing its velocity based on the positions of the other blue Boyds. And then you maybe have a totally separate red flock that is also flying around, that's coming out of core 1. And one flock knows absolutely nothing about the other flock. That would be an interesting next step. And then I think an interesting third step is to get those two flocks to see each other, which requires some kind of inter-core communication, right? The requirement for the lab is that there's one flock. There can't be two independent ones. So if you say, I animated 1,000 Boyds, but those 1,000 Boyds are in two totally independent 500 Boyd flocks, that doesn't count. That's 500 Boyds. What I'm interested in is the largest flock for which every member of that flock is taking action based on other members of the flock. One flock as opposed to two. Does that make sense? Okay. That's almost everything in this demo. There's one additional thread that I want to look at called Protothreads serial. One of the other aspects of this lab is I'm asking for you all to build some sort of a user interface, probably a terminal-based user interface that allows for you to change things like boundary conditions, specify the number of Boyds in a particular scout group, a biased group. What this user interface is allowing for us to do is input some number in the range of 1 to 7, and then it maps that number to a particular color. By the way, why only 8 possible inputs for the color? We'll talk about this in detail later on, but the reason for this is in order to get, so the way that pixel information is represented on this VGA driver is in a very long array. And a particular index of that array holds the color information for a pixel, or in fact, a couple of pixels. in order to fit pixel information for an entire 640 by 480 screen, the maximum amount of bits that I could fit in a conventional data type, that is to say like a car or a short or something like that, is 4 bits per pixel. And the one that's actually implemented here is 3 bits per pixel. So what that means is you have red, blue, green. 1 pixel of information for each of those colors. So that means you could draw a red void by having red on, blue and green off, a green void, a blue void, the combinations, cyan or magenta. You could have them all on, which will create white, or you can have them all off, and that'll create black. So you add all that up, and that's what, eight possible colors. Which means you're not going to create like really luxurious pieces of artwork here, but it's enough colors to implement like a video game or something like that, or something like this, right? And incidentally, Bruce modified this to add that 4th bit of color, which, suppose you have a bit to spend. You have 1 extra bit to spend on red, green, or blue. Which one should you add to? There's a right answer to this, fascinatingly. If you are building an interface for humans, I'll say. The answer is different if you're building one for white-tailed deer.
Green.
Green. We have more green color channels in our eyeballs, probably a consequence of being evolved to be around foliage. We're good at picking up, at discerning different greens. So if you have extra bits to spend them on green. And you would think that 1 extra bit of green wouldn't get you that much, but the color palette that unlocks is actually a pretty rich one. Just with a little bit of extra green information, you get a whole lot of different colors, a whole range of oranges. White-tailed deer are missing the green color channel, I believe, which is part of the reason that tigers are the color that they are. If you were looking at a tiger and you were a white-tailed deer, they actually do camouflage quite well with the perceived color of the foliage. Kind of interesting. They're missing a color channel. Some animals have additional color channels. So a lot of insects see in UV. So looking at a flower as an insect is a totally different experience than it is as a human. So in any case, I want to talk through this final thread. This is the one through which we can enter some sort of user information. So as always, we start with a PT begin. Similar to before, we're declaring a static int here called user input, where we're going to store the information that the user has entered through the serial terminal. We yield for a little bit. We then call an sprintf to put this message, Protothreads RP2040 v1.0, into this character buffer, pt serial out buffer. We then call this serial write, which I'm going to talk about today. So we could, one option here, one that you've all employed already, is to you could call something like a printf on this buffer, right? And then you would print the contents of that buffer out to the serial console. Printf is blocking, right? So that means this particular thread will block until printf has finished communicating that message to the serial terminal. We are communicating at a baud rate of 115200. To communicate, actually, this is a good time to start talking about this. So I want to talk in order to substantiate the conversation that we're about to have, I want to talk just very briefly about how UART's actually working in order to justify why that line of code that we were just looking at is such a clever thing. So start with information that you all know. How do you hook up a UART channel? It's mercifully simple, actually. There's RX and TX. The only gotcha here is to remember that if you're communicating between 2 devices, the RX of one attaches to the TX of the other, and the TX of one attaches to the RX of the other. Kind of makes sense. Whatever one device is transmitting, you want for the other device to receive, but it's an easy wiring mistake to make. If you make that mistake, you will not do damage to the system. Swap them. I can't think of a way that would damage the system. So how does a UART transmission actually work? UART stands for Universal Asynchronous Receiver Transmitter. Asynchronous suggests that there's no clock, right? So we were looking at SPI previously. There's a shared clock line between the sender and transmitter that they can both see, so that each knows when it should go access information on the data lines. Same is true of I2C. There's a data line and a clock line. There is no clock line in a UART channel. So the way that a transmission occurs is whatever device wants to send, say, an 8-bit character, the transmit line for that device is idle high. It sits high when no transmission is occurring, and it will indicate that it's about to start a transmission by pulling the transmit line low for 1 bit time. This is the start bit. This is the signal to the device that's going to receive the transmission to start its own clock. So this start bit phase aligns the clock on the transmitter and the clock on the receiver so that the receiver is accessing the data on this line at the correct times in phase with the transmitter, which suggests that the clocks on the transmitter and the receiver should be synchronized, or it suggests that it is sensitive to desynchronization, and indeed that is the case. These two clocks need to be synced within like 2% or so. So in any case, the transmitter drops this transmit line low, which is the indication for the receiver to start its clock. It then clocks out 8 bits and indicates the end of the transmission by pulling that transmit line high for 1 more bit time. So you can see that to transmit 8 bits of information, 1 character, it costs us 10 bit times. Seem a little archaic to anyone? It's a pretty simple protocol, right? It's an old protocol. This is, let me think about this. This is based on, I'm trying to remember my history. I believe that the story, why is this idle high, active low? This goes all the way back to telegraph machines, where it was a matter of convenience to have the data lines on the telegraph machine idle high so that if one physically broke, the symptom of that was more obvious, drop to ground. So this is idle high for that reason. It goes all the way back to this. And then its protocol goes back to telegraphs, I believe, right, Bruce? And the fastest that you could run a telegraph machine or a teletype machine was a baud rate of 110 bits per second. So now when you look at the available baud rates on a lot of UART channels, it's these somewhat bizarre numbers, 9600, 38400, 115200. Those are multiples of 110, the old fastest baud rate for a teletype machine. So it's an old standard. Each of these bits in this 10-bit transaction costs us 1 over the baud rate seconds. So if we're communicating at 115200, that's 1 over 115200. That's, you know, how many zeros is that? That's 1, 2, 3, 4, 5, 6, something like 8.5 microseconds per bit. So for a whole character, we'd have to multiply that by 10. Something like 80 microseconds. It's slow, right? You have some degrees of freedom here. You can configure the number of clock pulses per bit. So you could have a particular bit take 4 clock pulses or 16 clock pulses. Less clock pulses per bit means a faster possible data rate at the cost of possibly introducing more errors because you're sampling the data on this line less frequently per bit. Yeah, I think that's all I want to say about that. And then question?
What if you want to transmit multiple ones? How does that know? Oh, it's posted down. Oh yeah.
Yeah, so if you wanted to transmit all ones, it would be start bit goes low, 8 ones, and then the stop bit.
Does like the transmitter and receiver like know how many bits is going to be transmitted?
Yes.
Okay.
Yes. So it requires that in order for this to work. So because this is asynchronous, both the transmitter and receiver need to agree on how many bits are going to be transmitted. That allows for the receiver to know when to expect that stop bit. And they also need to agree on the baud rate. Each will allow for you to configure the baud rate to be whatever you want for it to be. But if, for instance, you opened a PuTTY terminal and configured your UART connection to the Pico to be 9600 baud as opposed to 115200, what you would see is either nothing getting printed out or unknown ASCII characters getting printed out. So they need to agree on these things. And there are a handful of, this protocol suggests that a few errors might occur. And if you go and look at the status registers associated with UART peripherals on essentially any microcontroller, you'll find error information in those status registers. And usually you'll find errors of the following varieties. So you might find some bit in the status register that's used to indicate that a framing error occurred. A framing error is one exactly of the sort that you just suggested, which is the receiver expects a certain number of bits coming at a certain rate, so it expects to see the stop bit at a certain time. If it doesn't see the stop bit at the expected time, it will throw a framing error. You may also get a parity error. If you have a UART channel configured to parity mode, what that means is that it will send, one of the bits will represent the parity of the data bits. Parity being, if you add up all the ones and zeros or do a logical combination of ones and zeros, you end up ultimately with an even number or an odd number. So you receive the data, you compute the parity of that data, you compare your computed parity to the parity that the transmitting device sent and ask if there's a match. And if there's a mismatch, you know that one of the bits got flipped. You don't know which one. And incidentally, if two of the bits get flipped and they get flipped in such a way that the parity stays the same, well then you don't detect that error, right? But it's a little bit of error checking. In any case, you might see parity errors in the status registers associated with UART channels. You might see an overrun error. So because this is asynchronous, the way that this often works in microcontrollers is the UART peripheral will be sitting there waiting to receive some character. And once it receives a whole character, sees a stop bit, it now has a character in its UART receive buffer, it will indicate somehow to the system that there is data available to be gotten from the UART receive buffer. It might throw an interrupt, it might throw a flag, it'll do something to indicate there's UART information here for you to come get. And then the system will go and get that data and clear the buffer so that it can be prepared for the next character to arrive. In the event that you don't go and process that previously received character in time before the next one starts to appear, you could get an overrun error. And then the other thing to just be aware of perhaps is these break conditions, which looks to the receiving device like an error. A break condition is the transmitter will hold this line low for longer than a character time. So what the receiving device will interpret that as is an all zero character followed by a framing error. But in some systems, it's nice to be able to exchange break conditions between one another. We use this, by the way, a clever hack of this in the remote learning semester for this particular course. In order to, Bruce put together a circuit that would allow for us to do a hardware reset of the PIC32. That is to say, pull the reset pin on the PIC32 low by sending a break condition. So, you have the UART transmit, the UART receive line going into the PIC32 connected also to the active low reset pin through something like a low pass filter. When no transmissions are occurring, that's sitting high, the system's on. When fast transactions are occurring, the filter prevents the pin from dropping low. If you send a break condition, it goes low long enough to pull the pin low and do a hard reset of the CPU. In any case, clever. Okay. I'm not going to talk about that. So then if we go back to the code, what we see after this sprintf is a serial write. This is here in place of something like a printf. A printf would sit and block until this whole message was written to the serial console, which, as we just talked about, that takes 1/115200 times 10 times the number of characters. That's a long time. What serial write does, let's just go take a glance at this quickly in the Protothreads header. Is spawn a child thread, this serial out pulled child thread, which
Spawn a child thread.
which will it looks at that buffer into which we just put the message that we would like put onto the terminal, and it will yield this, the child thread will yield until the UART is writable. That is to say, until it is possible for a transaction of a single character to occur. As soon as this condition is met, the thread gets scheduled. It writes one character out through the serial terminal, and then yields while that character is being written. So in contrast to printf, which will block until every character in that message is written to the screen, what this does instead is start writing a character, and while it's being written, yield the thread so that you can go about and do other stuff. And then as soon as that character is finished being written, this UART is writable will return true, or 1, will indicate that this thread is ready to be scheduled again, and it'll put the next message out onto the serial console. So to you as the user, it looks identical. It's behaving exactly like a printf, but what it's allowing for you to do is have other threads get scheduled in the middle of a print statement, because you are only ever printing one character at a time, and you're yielding while that is actually happening. Yeah.
How is it possible to release process resource when you're actually using it, saying that it's print stuff?
Can you ask that one more time?
If you're printing stuff to a serial port, then you're using process resources, but you're releasing it.
So we're using a UART hardware peripheral.
Yeah.
So it's an external peripheral from the RP2040. And when we call say a UART put character, what we're doing is sending a command to that external device to say, please write a character. It will go about and do its business. And while it's doing its business, we're yielding so that the ARM can run other processes. And then when that external device indicates that it's finished doing that character, we give it another one.
When you use, how are you scheduling this thread, or like how did you implement the thread, the scheduler?
So what we called in the source code was this serial write macro. What the serial write macro is doing is macros are textual replacements, right? So it's replacing serial write with this string of text. What this string of text is doing is spawning this thread as a child thread. So this is slightly convoluted, and we're down a level of abstraction that is probably of immediate sort of practical relevance to you, but it's interesting to know. So I've mentioned before that we don't want for threads to exit. So every thread that we're scheduling in our main code has some while one loop that's getting scheduled and scheduled and scheduled and scheduled. The caveat to that is Protothreads allows for a parent thread to spawn a child thread. So you can have a thread that it itself generates a child thread. That child thread, we do in fact want to exit. So in the parent thread, when the child thread gets spawned, the parent will sit on that line of code where the child was spawned until the child exits, at which point the rest of the parent thread runs. So you can see that one of the unique aspects of this child thread that we're spawning is there's no while one loop here. We go through, and when this is spawned, we start the thread, and then for each character in that serial buffer that we want to write, we write the character, yield until that character is finished being written, write the next one, yield, write the next one, yield. When we get through all of them, we exit the thread, which means that when we exit that thread, we will move past the serial write line in our source code. Yeah.
I just wonder, like, character.
Oh my God, sorry. Yeah.
I just wondered that, like, you put a character and then you yield. Like, when the UART is available again, then it will, like, write another character. But, like, how fast is it scheduled? Like, which place would it be put in the FIFO or something like that?
How fast does this get scheduled again?
Yeah.
Is that the question?
It's priority.
So unless you change anything, all of the threads will have the same priority. So what will happen is we put a character in yield. As soon as that character is finished, this condition is satisfied, and this thread will indicate to the scheduler, I'm ready to run again. It won't actually get to run again until the scheduler gets back to that thread and asks it. So it is suppose that you called serial write, you wrote one character, you yielded, and then some other thread ran that retained control of the CPU for a second, then you wouldn't see the next character get written for a second. Because it's a non-preemptive threader, none of the threads will interrupt the other threads. So a particular thread will run until it yields. And then when it yields, the scheduler will go to, in a really simple round robin way, it'll just start looping through the other threads and asking, are you ready? Are you ready? Are you ready? It'll go through all the rest of them. Whichever is the next one that reports, yes, I'm ready to do something, it's allowed to do something until it yields, and then we go to the next one. Make sense? And then one of the only other things I wanted to mention while we're in this Protothreads header is, if we scroll up just a bit, we will find a few other things that Bruce added here, and in particular, so this is all, I'll just remind you, documented on the Protothreads webpage. The whole API is documented, and you should familiarize yourself with it. But one of the things I just wanted to point out, because it's perhaps relevant to you this week, is if we scroll up and take a look at, so we've seen PT yield microseconds. You can see when we look at the implementation of this, that what's actually happening under the hood when we call PT yield microseconds is we are setting the value of some variable equal to the present value of the microsecond timer plus our desired delay time measured in microseconds. And then we're yielding until the value of that microsecond timer exceeds that threshold. Does that make sense? So when we want to yield for, say, 100 microseconds, we say, okay, yield until the timer is greater than or equal to the present time plus 100 microseconds. Yeah.
What's the meaning of while 0? I mean,
So this is a do while loop. So what this means is this will get executed regardless of, yeah, Bruce?
So if you're gonna put complicated logic in a macro, it's a really good idea to force it to be an atomic block, to be an inseparable block. Putting a do curly bracket, code curly bracket while 0 enforces that it has to be kept as a unit and will execute precisely once.
And I'm pointing this out just so that you can see how it works. Potentially of relevance to you is this PT yield interval. What this does something very similar, but instead of saying I would like to yield for 100 microseconds, what this allows for you to specify instead is I would like for this thread to be scheduled every 100 microseconds, which means suppose that it takes 75 microseconds for the other content of the thread to actually execute. The yield time in that case will be 25 microseconds, not 100. So it adjusts the yield time in order to make certain that the thread is scheduled at a regular interval. The way that it's doing it, incidentally, is you first call a PT interval init. This would go in the initialization part of that particular thread. And all this is doing is declaring a static unsigned int, which we're calling the interval marker. Since we're not specifying an initial value for this, it's initialized to 0. We then come down, and the first time we encounter a PT yield interval, this will yield until the microsecond timer's measured value exceeds whatever the value is of this particular variable. The first time through, that's going to be 0, so this is going to run. But right after we get past this yield until, we update this PT interval marker with the current time plus our desired interval time. The thread will then go back to the top and execute everything else. And when we get back to the PT yield interval macro in our thread, it will yield until the value of the 32-bit microsecond timer exceeds the value of this interval marker that we set the last time through the thread. So, which is just to say that, it is accounting for, because we are setting the value of this threshold before going back through the loop, instead of at the end of going through the loop, we're enforcing an interval rather than a delay time. that clear? That felt a little convoluted as I was saying. Okay. That's all I got for today. I think we're out of time. But I'll see the Wednesday folks very soon. See the rest of you on Friday.